In this video, we will learn about another variant of finite automata, that is epsilon NFA. We have already discussed deterministic finite automata and non-deterministic finite automata. In this video, we will explore epsilon NFA. So let us first understand what is the difference between all these three. Formally, we can define epsilon NFA as phi tuple, that is machine M or any automata M is given by phi tuples capital Q, sigma, delta, Q0 and capital F. And same tuple we have used for representing DFA and NFA. And if you remember, there was only difference in transition function in case of DFA and NFA. In this tuple, capital Q represents set of states in the given transition diagram. Sigma represents set of all the input alphabets. Now the difference between DFA, NFA and epsilon NFA lies in the transition function. The way transition function defined is the only difference. Delta defines the transition function. For DFA, the transition function is defined from Q cross sigma to Q. That means if we are in some state Q, and if we read some input alphabet from the set sigma, then we are moving to some another state Q. And there will be unique transition for each input from every state. For example, from Q0, if we read A, then we are remaining in A. And if we read B, then we are moving to Q1. So there is only one transition for input A and B from Q0. Same way from Q1, if we read A, then we are moving to state Q2, and on reading B, we are remaining onto the same state. So as you can see that our input is actually Cartesian product, that is the one tuple, current state and the current input, and output is the next state. So this is defined as a Q cross sigma to Q. In case of NFA, the transition function is defined by Q cross sigma to 2 power Q. Because here transition is non-deterministic, on any input we can move to multiple states at a time. And these multiple states could be anything. It could be no state, it could be any one state, it could be any 2 states, 3 states. So in fact, we can move to the power set of the given set of states Q. And that is why the transition function is defined by Q cross sigma to 2 power Q. 2 power Q is the power set of state Q. As we can see in this transition diagram, on input B from Q0, there are 2 transitions. One is on Q0, one is on Q1. So there is a non-determinism. From state Q1, if we read A, it remains on state Q1, or it can move to the state Q2. So that is what NFA. We can have a multiple transition from the same state for the same input. And in case of epsilon NFA, it is the simplified version of NFA in fact, where we can have a transition from one state to another state without reading any input symbol. So this is NFA, but this is the additional state, that in NFA, we have to read some symbol to move from one state to another state. Whereas in case of epsilon NFA, epsilon is a null. So without even reading anything, we can move from one state to another state. So as we can see in this diagram, from Q0, without consuming any symbol, that means by reading the epsilon, we are moving to state Q1. So we have not consumed any input alphabet A or B. So the transition function for this is defined by Q cross sigma as well as epsilon. So that is sigma union epsilon. And again, it's an NFA. So the output would be one of the state from the power set of input states, that is 2 power Q. Remaining things are same. Q0 is the initial state of the machine, and capital F is a set of all final states into the given NFA or the given machine. So this epsilon NFA will not bring any power, but it will simplify the process of constructing NFAs. DFA is faster in recognizing string but slower in construction. We can quickly construct NFA, but due to non-deterministic behavior, the parsing of string is slower. So what normally people do, they construct NFA and then they convert it into DFA. Fine. And again, construction of any machine or any NFA can be further simplified by introducing epsilon transition. So what we can do is we can go for the epsilon NFA first. We can convert it into NFA. NFA we can convert it into DFA. And we also know how to optimize the DFA. We can minimize the states of the DFA. So when we take the concatenation of any alphabet with epsilon, that is epsilon concatenation with A is same as A concatenation with epsilon is same as A. So we can consider this epsilon as a null or the neutral symbol. It doesn't add anything into the string even if we read it. If we want to generate NFA for the A, alphabet A, then it can be given like this. We are reading A from the Q0 and we are moving to the final state Q3. The same NFA we can rewrite in this way, that we will read epsilon symbol from Q0 moving to Q1, and from Q1 we are reading A and we are moving to Q3. So it is same, because we already know that epsilon concatenated with A is A itself. So even though representation of both NFA is different, but they represents same language, that is a alphabet A. And we can also rewrite it is like this. From Q0 read epsilon, we are moving to Q1. From Q1 we are reading A and we are moving to Q2. From Q2 we are reading epsilon and we are moving to Q3. So ultimately this NFA will also read A only, because epsilon is not considered in a string. The purpose is to show you that you can read epsilon anywhere, but the language should not change. So this will give us a great flexibility in construction of NFA. So epsilon NFA are even simpler than just NFA. Let us try to construct epsilon NFA for some of the language. Consider the language where strings are ending in AB or BA. So we are already familiar with how to construct the strings ending in AB or BA. Right? So this is the language. L is equal to AB, BA. Red symbols are for strings ending in AB, and blue symbols indicate strings ending in BA. So last two characters must be either AB or BA. Before that it could be anything. So this is the automata for string accepting AB only. This is the automata for strings accepting BA only. Now these two strings AB and BA can be at the end. Okay. After that we cannot read anything, but before this we can read anything. And if we put epsilon transition here, then this automata is accepting string either AB or BA, only two strings. But what we want is, we want to generate all the strings which are ending in AB or BA. So the partial NFA we have already generated. Now what we can do is, before these two strings AB and BA, we can read anything. So we can simply add the arc of A and B here, and then by consuming epsilon we can go either of the branch and we can have an appropriate string. And this is the transition table. Now we have one more column into the transition table, that is for the epsilon symbol. So when we read epsilon from Q0, we can move to set of states either Q1 or Q4, and corresponding entries are shown in the transition table. Let us construct epsilon NFA for regular expression A star, B star, AB. That means the strings in this language would be either AB. A star means 0 or more A. B star means 0 or more B, and then AB. So ultimately we have to read some n number of A followed by some m number of B, and at the end there must be AB. So let us construct epsilon NFA for that. So this is the initial string, the initial state. By giving the self loop, it says that we can read any number of A here. Once we read A, and when we want to do, when we want to write down the transitions for B, we will go to another state, because we cannot put arc of B on same state. Otherwise it will be reading A, then B, then A, then B, then A, then B, something like that. But our language says that we have to read out first n number of A. Then we have to read all the B's. You cannot alternatively read AB, 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 right? You have to read first some m number of A's, so that we can simulate using the self loop. Once you read B, you are not allowed to read A from the A star. So we are going to another state without consuming any symbol. And here we are generating a self loop of B. So we have some A, then we are going to Q1, then again we have some B, and at the end there should be A and B to reach to the final state. So this automata ensures that it will only read the strings which are ending in AB. Next, AB whole star, AAB whole star. It means you can have 0 or more occurrence of AB followed by 0 or more occurrence of AAB. Right? So AB always should appear in pair, and after that AAB should always appear in pair. And as there is a star, we can also go to final state without reading any symbol, because it star means 0 or more occurrence. So even if we do not have any alphabet, it can go to the final state. So initial state is Q0. If we read A, it should go to the non-final state because that is not allowed. But when we read B, that is acceptable. Fine. So and we have ensured that this will keep looping AB, 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 etc. And there is a star. It means we can also totally ignore that AB part. So what we are doing is we are simply doing like this. If we even have an epsilon, we can go to the final state. We also have to simulate double AB. So if we read first A, second A, and third B, then we are coming to the final state. And this is in a loop. So if we have any time only double A, we are in non-final state. But when we read B, we are in final state. So even without consuming any symbol also, we can go to the final state from Q0. After reading m number of AB, we can come to the final state. And that can follow any number of AAB, AAB, AAB strings. So this is epsilon NFA for given regular expression or the given language. Consider the another example that a language contains strings over alphabet A, B, C that are missing at least one letter. So whatever strings are in language, they all should be such that one letter is missing. Q1 produce all the strings over alphabet A, B where C is missing. Q2 produce all the strings of alphabet B and C where A is missing. And Q3 produce all the strings of alphabet A, C where B is missing. And our language is combination of all this. So either we can have transition towards Q1 where it will generate all the strings of AB, or epsilon transition on Q2 which will produce strings of B and C only, and similarly we have a transition for state Q3. So this is the desired NFA. You can see that how easily we can construct NFA for any given language with the help of epsilon transitions. Fine, that will add, see, power of DFA, NFA and epsilon NFA is same. That means they can produce same set of languages. The thing is that epsilon NFA gives more flexibility compared to NFA. NFA gives more flexibility compared to DFA. But DFA takes less time for recognizing string, NFA takes more time, and epsilon NFA takes even more time. So time wise DFA is better, and from the point of construction epsilon NFA is better. Thank you. That's it for today folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.